you've got your machine. Okay. Well, today I want to talk about differentiation. Yesterday, I don't know how many were, since everybody's abandoned and I can't see who you are and stuff, I don't pay attention to who's out in the audience on a given day, just because I don't really know you all yet. So I'm not sure who, I think I know who was here yesterday and who wasn't, but I wouldn't swear to it. What I tried to do yesterday on the blackboard was just sort of play around with the idea of derivative. The derivative is a limit, and I kind of stumbled around a bit. That was on purpose, because you got to try to kind of understand what we're talking about. I have a handout that I gave people who are here, and as I say, I'll be putting that up on the screen in a minute, and also putting it on Blackboard later for everybody, which does a much better job, let's say, than I did yesterday of trying to explain what we're doing. Okay, but I want to, while we have the blackboard, talk about things. First of all, with a derivative, you have two basic things. You have a function and you have a point. I like to use the point x naught because I like to say it's fixed. We could use a letter A or anything else to say it's fixed, but I like to get you thinking about when you see an x naught, you know it's not varying. Even though it might be anything, but once you choose it, it's fixed. Okay, and so incorporated in the function f is a domain, and so what you also have is some set D, might be an open interval, it might be the whole real line, it might be the positive numbers, it might be all kinds of different sets, but we have to know what the domain is, so we know whether or not the point, for example, x naught is in the domain. If the point's not in the domain, then you don't have a limit. Okay, or if you have a limit, let me change that. You don't have continuity. And again, for differentiability, we only differentiate at places that are in the domain of the function. Okay, so anyway, this notation, the prime is the sort of universal thing we say for a derivative. And so if I see this and somebody says, what is that? If you're, walk in the room and you see that, I would think that somebody's saying the derivative of the function f at the point x naught. That's how I would interpret the symbolism. It may not be true, but that's how I would do it. And somebody said, well, that's not what we're doing. Okay, if they have a different symbolism, fine. But this is kind of the universally recognized symbolism for the derivative of a function at a point. There are other symbolisms which we will be getting to. And maybe you use other things in high school if you had some of this. In any event, it is defined as a limit. Okay? So not only is the function in the domain, but it's also an accumulation point of the domain. You have to have other values of the domain being able to get close to this value x naught. And so it has to be an accumulation point. That's why we can use limit. And then the definition says that we have what's called a difference quotient.
Dr. Brady?
Yes. Somebody wants in. Yeah, thank you. If that's what your comment or.
Yes.
Yeah, thank you. Two people actually. Okay. Thank you. Sorry for you guys. I'm turning my back on you, but it's not personal. Okay, so this is the basic idea. Now, what we're going to try to do is to develop things so we actually use the limit concept as little as possible. All right, because we try to use that like the foundation of the building, and then we're going to build on the building. And you might not see the foundation after a while, but what you'll see is the things we build on top of it. So, but this is a definition. Now, there are equivalent definitions. I gave you guys a handout that said equivalence. It was like a 2-page front and back kind of thing. And so there's an equivalence. And that is where you change things to h going to 0. And that looks like what I'm now writing instead of what I wrote before. This is also the same thing, as I said, you can see that if by using the equivalence we did before. Going from x going to x naught is the same as h going to 0. Now, what's the key to that? It's not part of this because these things stand alone, but basically we think of x minus x naught as being h. And so basically, if you think that way, when x gets close to x naught, the difference gets close to 0. When the difference between the two gets close to 0, then one's approaching the other. That's the idea. And over here, you're replacing x with x naught plus h, because x naught plus h would be x. And so these two things go hand in hand. Sometimes we use one, sometimes we use the other. Sometimes you could use both. And if you do lots of problems, which I highly recommend, you'll get a feeling for which one you like best. And so sometimes you have a choice and you say, oh, I like this one. You do that, fine. Sometimes you can do it two ways. Sometimes you try it one way and it's like, this doesn't get me anywhere. So then you try to switch over and do it the other way, and hopefully the other way will do it for you. But you've got to do a lot of problems to get the experience to decide which way to go when you see something like this. Okay? So now there's something else we're going to do. This is another part of the equivalence. You may remember, and I'll write this with G instead. When we did limits, we had like continuity, or that was when we wrote something like this. If I just had a limit, I would write something like L over there on the right side. But we had a theorem that said this is the same as the following. And I stopped here by the colored chalk and the fingerprints. Anyway, this is the same as the difference of these two things being 0. So as the value g of x approaches g of x naught, the difference of the values approaches 0. This is another thing we do. And since this morning, we're going to use both of these ideas in what we are going to do. And you need to get familiar with them, so at any moment you might say, okay, instead of doing the one, I'm going to do the other. Okay? Because again, it's always good if you have two ways to do something. Okay, so what does that do for us over here? Well, we could, instead of what I've written above here, we could write the limit of f of x minus f of x naught minus, well, I'll do this twice, but twice here. One would be set here, put out and everything. I hope you can read at home. Basically, by the way, somebody I talked to on the phone last night. Are most of you at home, and that goes for you guys here today, can you zoom up on the keyboard with your computer? In other words, I can press a button here and zoom up on things. If I press Control here on my Macintosh, I can go and look at the screen much more closely. Do you guys do that?
I don't know how you do that.
Okay. Well, not everything does it, but you need to find out if yours does, because I know this is hard to read. But if you can, right here, I can zoom up on it and look at it real carefully, and it's easy to read. Okay. So you need to make sure that whether your computer or your phone or whatever it is you're talking about, can it zoom? Okay. Because most of them can, even though you might not have used that capability. Okay. So you might look into that, because one of my problems that I feel bad about is not being able to bring this close enough so everybody can see it. That's why I go to the notes, so everybody, at least it's there. The trouble with the notes is then you can't see me and all my dynamics and all that. Not that that's a good thing, but anyway, that's the way it is. Okay, so why did I say here at the bottom that I'm going to do it twice? And that's because what I want to do is to put this thing in brackets into one thing with one denominator. So I'm going to erase this thing here. This was just an equivalence that's in our notes in the past. And I want to write that down in this form, and I hope you're going to appreciate a little bit why we're writing it this way. Because I'm hoping that there'll be some light at the end of a tunnel, or there'll be some clarity or some like, oh, that's interesting, or something that comes out of what I'm doing here. So all I did was take the thing that was on the bottom of the screen over there and put it up on this blackboard with one common denominator. And I'm not done, I have to say it equals 0, but that is putting the thing together in one limit. Now, if you guys absorb that, I'm going to change it. Okay, I ought to write another time, but I'm worried about you seeing everything. And so I think this is as visible. By the way, one of the comments is strange. You guys ought to come up here and see. This one, I'm a mirror image of this one. So on that one, right is left and left is right. On this one, left is left and right is right. And so when I look from one to the other, it's like, I thought I was over there, okay? So I just started to tell you that on the left-hand side and the right-hand side, I looked down, it was the opposite, and I go, oh, okay. Anyway, what do we want to do with this thing? What I want to do is bracket out this part right here, which will change the inside part to a plus, okay? And I want to say, just suppose I write this down by itself. Okay? Suppose I just write the thing down by itself and set it equal to y. Okay, I just decided to do that. Can you tell me what this is? It's an equation of something. It's an equation of a straight line. Remember what the equation of a straight line was? Slope m. So, okay, what's the equation? If I have a point x naught, f of x naught, and a slope m, the point slope equation is, I'm hoping everybody can see this, is this. And that equation is the same as this equation. If the m is this thing right here. If this is the m, then that's the equation of a straight line with slope m passing through the point x naught, f of x naught. You're supposed to know from high school or someplace else the equation of a straight line. So this thing up here in this derivative concept, the thing I put in brackets here is actually not an equation, it's an expression. But if I equate it to y, I get the equation of a straight line. So what is this limit saying? Okay, it's saying that the thing I'm going to put in the box now, this is the function value. And the thing in the brackets is the value of the y value for the straight line. And we're talking about the difference of the two. That's how they differ, because the difference is how much something differs. Okay. And there's something else. The numerator and the denominator are a fraction, and the limit is 0. Now, what's the limit of a denominator? As x goes to x naught, what does x minus x naught do? Goes to 0. So in this expression, and in all of these expressions with derivatives, you have the denominators going to 0. Here it's going to 0, here it's going to 0. So when does a fraction make sense? When the denominator goes to 0. The numerator must go to 0. If the numerator goes to 6, then you got 6 over 0, which is infinite. Doesn't make any sense. So the only way that this can be 0 is that the numerator goes to 0 and while the denominator goes to 0. Okay? And more than that, when is a fraction close to 0? how big is the denominator compared to the numerator when you have a fraction that's very, very small? The numerator is really small compared to the denominator. The denominator is big compared to the numerator. Okay? So that's saying, however far apart the x and the x naught are, these two values are much closer together. They're so close that the fraction is almost zero. That says this thing is really close to this thing. And that says the curve is really close to being approximated by a line. And that's why we call it the tangent line. Because it hits it at one place and it's very close to it nearby.
Professor Brady,
Sir.
could you read on the right side of what you've written? Because some of us are having trouble with the expression of seeing it.
Okay. Tell me where. Can you see what this is? Or you want me to move? Maybe I can move it over there. Everybody see over there what it is? Is this clear enough? Can I erase this?
I can see the left side, yes.
Anybody object to me erasing this at all?
Dr. Brady, I can't read the bottom line on the left. Can you read the bottom line on the left out loud?
This one?
Yes, the bottom one.
Okay, let me redo it. Take a little time, but that's what I want you guys to tell me because I hate this. Okay? I want you to get it, and if you can't read it, that's why we're going to go to the notes in a little while. All right? But let me replace. The top part was just the derivative part. You guys seem to say you can see that. So let me replace this bottom thing with the limit f of x minus f of x naught over x minus x naught minus f prime of x naught. All I did was move that from the right-hand side into the limit concept. That's what is down there. Okay. And what I said now from this is if we make a common denominator here, here's a thing subtracted from a fraction. If I algebraically make a common denominator, then the first thing that happens, the common denominator you have to bring in, I have to multiply by x minus x to the 0, numerator and denominator. And so first of all, I have all this now in brackets. Okay, sorry, this is x naught. Then, but the next thing I did, is this visible up here for you guys at home?
No,
Is this okay or is this dim too?
we can't really see anything of what
Okay.
we're looking at.
So the next thing I did, I'll rewrite it. Now, can you guys see this?
Yes.
All right, the next thing I did was bracket the minuses together. And this needs to have an x naught in it. Get over there. X minus x naught. I bracketed these things together over one denominator. And then I made some comments because, so if you couldn't see that either, one more thing. If I make an equation of a straight line that passes through x naught, f of x naught, with slope f prime of x naught, this is the equation of such a straight line. And if you look at it, the part here is exactly what's here. And so what we're saying is because the limit is 0, the numerator has to approach 0 much faster than the denominator, but they both do, so that the fraction goes to 0. And that basically saying is this value is very close to this value, which says the straight line and the curve are almost the same. That's what we mean by derivative. And we should be concentrating on the line, not the slope. Because when you get to Calc 3, it turns out there is no such thing as a slope, but there are things like tangent planes. And so we ought to be talking about the thing that's like the function rather than the slope of the thing that's like the function. But for this semester, we'll be concentrating on getting these numbers called slopes. Later, we'll be concentrating on getting the line that's a slope that has that slope. Okay? You don't need to worry about that yet. I'm just warning you later that we change emphasis later. In other words, the first people who did this got the wrong idea. They got the wrong emphasis. Later, we found out to be able to go to more dimensions, you've got to think differently. And once you think differently, then you can see why they thought wrong. But we'll get to all that later. Anyway, so this is hopefully reproduced. I hope you can see this. And from now on, I'll try to stay over here. It makes the lecture real bad because I'm always writing on top of what I had. I'm sorry about that, so don't complain in teacher evaluations. I'm kidding now, of course. I won't see the teacher evaluations until after the class is over. Therefore, you can say what you want. Now, I'll tell you a secret. I'm being recorded, so this is a lie. The recorder, I can change your grade later. That's true, but not ever possible. I wouldn't do that. Okay, so let me go to the share screen so that some of you who haven't been able to read so far can't complain about that anymore. Yeah. Okay. So what I'm going to look at right now, hopefully, I'll move it over so you can see it. This is what the people who are here today have in their hands. Okay. Now, the first couple of pages are, and by the way, what this is, some of you may know I'm writing a long book right now on page 2304. And this happens to be chapter 46 or part of chapter 46 in the book. And at 9 o'clock this morning, I thought, well, why don't I give them a little bit of the chapter that I wrote? Okay. So I'm hoping that I got out of the material you're getting any references to stuff that's, if it's chapter 46, it might refer to chapter 45 and things like that. I tried to remove all that so that you'd think I wrote it just for you this morning. Okay. But I started doing it at 9 o'clock, and so I did it kind of quickly. It's only 20 pages long, but it took me a little while to do the 20 pages between 9 and 10:30. So anyway, this first few pages is just talking about the idea of, well, I wrote it here, the mathematics of how things change. What calculus is about is describing how things change in all kinds of different ways. And so I thought I'd bring in here how the original people who did this, how they were thinking. I don't really know because they're all dead and I didn't talk to them, but what I think they were thinking to develop this stuff. So the first couple of pages, I think are just, I don't want to talk about it right now. I want you to read it and then we'll talk about it if you have questions, okay? And so really it's page 3 where we want to start. And now you guys, if you couldn't see the screen before, except for the letter capital F, I wrote up on the board this limit of f of x minus f of x over x minus x naught already. And down here, later on the page, you have the x naught plus h. This is what we already did on the very first part of the blackboard I wrote this morning. That's explaining how we write the derivative in terms of a limit. And that's page 3 of these notes. Okay, and then page 4, you can kind of skip at the moment. What that is another way to talk about derivatives, which is really clever. First done by a man in I think Czechoslovakia named Theodore in 1920, but you don't care about any of that. What you do want to look at is the bottom of page 4, the geometric interpretation of derivative and tangent line. That's what I just talked about that you guys had trouble seeing. Okay, so page 5 is trying to talk about what I've already been talking about this morning. All right, so if you had trouble seeing it, I'm moving down on the page to the bottom, page 5. You should now see in the middle of the page the same kind of definite brackets and stuff that you hopefully could see on the board. So once I get this in Blackboard, or if you review the video, you will have all of this, whether or not you could see it very well earlier this morning. Okay, so What we want to do is go a little further here. And so where I am for you guys here, I'm on bottom page 6 now. I've kind of moved things up. Derivatives are always at one spot only. We always define a derivative at one place only. That's how it's defined, point by point. Now, somebody noticed, when they were doing this, that if I do the same function at 2 different points, I get 2 different derivatives. And we can prove uniqueness. We can prove you can't get 2 different limits and things. And so you begin to associate with a point its derivative. And as soon as you do that, if you paired those up, you're making a relation. Relation is sets of ordered pairs. If the relation has the property that no 2 distinct ordered pairs have the same first component, that's called function. So what you get out of starting to do this, if you take one function, like the sine function, and I say, what's the derivative of the sine function at pi over 2? That's one place. I get an answer, which we'll be getting later. I might say, okay, what's the derivative of the sine function at pi over 4? Or what's the derivative of pi over 3? Or what's the derivative of 0? When I start listing answers, that becomes functional because you're pairing up pi over 4 with its derivative of the sine function, and pi over 2, you get a function. So we get what's called a derivative function, okay? And we're going to learn that the derivative function of the sine function is the cosine function, okay? We'll prove it by doing it one point at a time. And the one point at a time will involve these limits, okay? That's going to be the game. But what we're really looking for, when I say I want to take a polynomial and I want to differentiate it, it turns out that the derivative function is another polynomial. But each derivative is a pointwise thing. You take a derivative at 3 or at 17 or at -5, okay? And sometimes derivatives don't exist. But anyway, we go from the idea of differentiating one point to saying, hey, can we do it at every point in an interval? Or can we do it at every point in the real numbers or whatever? And if we can, we get derivative functions. So what's at the bottom of page 7 is derivative function. And it says if f is differentiable at each point of a subset S of a domain, then we denote the function by f prime. In other words, we erase. And so I'm going to write this big, well, you guys can't see it. I'm going to write a big F prime here without the x naught, without the parentheses. That's the name of the derivative function. So we basically erase the of x naught, the parenthesis, x naught parenthesis from the thing, and we name the function by that. Okay? All right. So what's the very bottom of that page? We can have derivatives from the left and from the right. How do we do that? Well, we just limit the x approaching from the left or the right. It's a limit. And so we can stay on the right of everything and approach from things that are too big, or we can approach from things that are too small. Okay? We can have left and right hand. So what, if you think about yesterday, we had the absolute value function, remember? And that has the absolute value point is like a V. All right? If you would approach 0 with a V, the V, I can't show you on the blackboard now because you guys are looking at paper there. Anyway, but people here in the class, they can see me making a V. You just have to try. I guess you can see me in a little picture making a V. Make a big V. Anyway, if you do this kind of thing, the derivative exists from the left and right because from the left and right you have straight lines. And we're going to find out that the derivative is a slope, and the 2 straight lines have slopes, and therefore they have derivatives. So approaching from one side, you get a slope that is negative, and approaching the other side, you get a slope that's positive. Okay? But the derivative function does not exist for negative and positive. It's actually 2 straight lines, horizontal lines, that have a jump discontinuity at 0. We're going to talk, I'll put all that on the screen later. All right, I'll put it up. Anyway, so, but We're not going to concern ourselves with it too much right now, but we can talk about derivatives from one side or the other. We can also talk about infinite derivatives. So everything that you've been studying about limits, they can be infinite or finite or all that works for derivatives because they're just limits. Okay, so we'll get more into that later. And the biggie, one of the biggie things here, and I'm going to get off the screen and write it on the board, but for you guys, well, maybe I don't. Maybe I stay, let's leave this up here. What I'm going to write on the board for people here is the stuff that you guys can see on page 7. Okay, now maybe if I think about it, everybody here has a copy. So if you guys will all look at the proof on the bottom of page 7, for you who are here also, I won't have to write it on the board. If you look, I want to prove that if a function is differentiable at a point, then it's continuous at that point. So differentiability implies continuity. That's what I want to prove. So what's limit? What do we do for continuity? We talk about the limit of f of x equals f of x naught, if you remember. Well, I want to do the limit of f of x minus f of x naught is 0. If I can prove the limit, and if you look at the bottom of page 7, the last expression there, the very last thing on the page is 0 with a period. If you look up all those equal signs up 4 lines, you'll see the limit of f of x minus f of x naught equals, and then the bottom line is 0. That proves function is continuous. How did I get there? Well, you take f of x minus f of x naught, and algebraically, you multiply by x minus x naught in the numerator and denominator, which is the number 1, so it doesn't change anything. And then I slide the denominator over under the f of stuff, and I get a quotient. And then I use the fact that the limit of the product is the product of limits. So instead of the limit of something multiplied to something else, I change it to 2 products, the limit of this times the limit of that. You can see that. And the limit of the first one is the derivative of the function. That's why you see the very bottom line, f prime of x naught. The limit of the other is 0, so this comes out 0. And this is a proof that differentiability implies continuity. Okay? That's a very important concept we're going to find out. Whenever functions are continuous, you can do all kinds of stuff with them. So the fact that differentiability implies that will allow us to do all kinds of good stuff. Okay, now I'm moving down to page 8 here. And 8 has to do with the absolute value function. So if you didn't see everything I wrote on the screen about the absolute value function yesterday, here is the stuff I wrote yesterday. This is even more than I wrote yesterday, but this is about the absolute value function. And what you learn about it is it's a continuous function that is not differentiable at one spot. Okay, and so you can have continuity without differentiability. But if you have differentiability, you will have continuity. And the next, I don't want to talk right now about this, is domain endpoints. You guys can read all this, and some of you will have to study a little bit. But I want to get down to some properties now, because we don't really want to do this all the time. So suppose I know what a function does at, say, 5. As x approaches 5, I know what the derivative of the function is. What do you think will happen if I double the function? In other words, instead of f of x, suppose I think of 2f of x. What does that do to the derivative? If I multiply the function values by 2, what's that do to the derivative? I don't know. That's what we got to talk about. So if you look at page 10, okay, the proof of number 1 on page 10 says, if I have, I'm using now a cursor for people at home. If you have a function CF, and those of you here, you can see this right under the proof of 1. CF prime, the derivative of a constant times a function at x naught. That's how you read what I'm using the cursor on here, is equal to the limit. I just wrote in what it is. It's a difference quotient. But since you have C common here, how do you define a constant times a function? You define it to be the constant times the function value. So then we have a constant C. I can factor it out. The limit of the constant is just a constant, so I can go ahead and do that. I'm left with the derivative of the function, which is this. And so what we learn is, if I have 2 times a function, and I know what the derivative of the function is, I know what the derivative of 2 times it is. It's twice. So you can take constants out of the derivative if they're multiplied to the function, not added, multiplied. Okay? So number 2, though, says, what if I have 2 things I know they're differentiable? What about their sum? And the answer is the sum of the derivatives are the derivatives of the sum. Okay? Now, once we know, for example, how to differentiate a power, like f of x equals x squared, f of x equals x cubed, f of x equals x to the 10th power, once we learn how to differentiate such functions, then if I have twice one of those, I know how to differentiate those. And if I have the sum of 2 of them, I know how to differentiate those. So what you learn, once we learn how to differentiate x to the 10th power and x to the 9th power and so on, we will know how to differentiate polynomials. A polynomial is a sum of powers of x times constants. So once we know one more fact there, we'll be able to say what the derivative of a polynomial is. Okay? So in this page 10, I'm telling you how you differentiate a sum and how you differentiate a difference. And it gets a little more complicated all the time, but not so bad. It's kind of straightforward. And I'm hoping you can just, all you guys home and here can read that. And then I prove it a different way. Remember, I said to you, there was a page we skipped. I think it was number 3, page 3. I said there's another way to do it. I'm writing a book, and so I'm elaborating on some stuff here. Okay, so I say it's about time to start doing some elementary functions, the ones we know about. Yesterday, we talked about the constant function, if you remember. What's the derivative of a constant function? It's 0. What's the slope of a straight line that's horizontal? 0. What's the graph of a constant function? A horizontal line. It all starts fitting together. At each point of a horizontal line, the slope of a tangent line. Now, if I have a horizontal line, it is the tangent line. So this is an example of, see, when you think of a circle, what you learn in geometry, when you have a point on the circle and you talk about a tangent line, that tangent line only touches the circle once. And so you learn geometry, that's what you think. The word tangent has to do with the word touch, by the way. All right? But if I have a horizontal line, the tangent line is itself. It's the horizontal line. So the tangent line touches the graph at every point. So it's only circles where you might have it only touch once. When I say only circles, there may be some other things like that too, like an ellipse is similar. But a lot of things, the tangent, you're talking about what happens locally. Locally, it only touches once, maybe, but then later the graph will come back and it'll hit it again, but it may not be tangent anymore. Okay? So you have to be careful about generalizing from something you may have had in high school, because we're talking here about local concepts. Now, anyway, yesterday we talked about derivative of the constant function. I also talked about derivative of the identity function. That's proposition 212 here. And we can then generalize a little further and talk about what about the derivative of the function given by ax plus b. There's a couple of ways we can do that now. If I know what b does, and I know what x does, and I know what constants times functions do, ax plus b is the sum of 2 functions that are differentiable, one of them which has derivative 1 and the other one which has derivative 0. And so you can piece together, without epsilons and deltas and stuff, you can piece together the derivative of this affine function, ax plus b. Okay? The derivative is a. If I have ax plus b, the derivative is a. So if I differentiate the function 3x plus 2, the derivative is 3. Now, I told you a while ago we do this at every point. The thing is, for these functions, it's the same answer for every point. And so while you should do it at 1 and 16 and minus 4, you'll find out every time I do it, I get the same answer. So the derivative is a constant function. And once you know that, we don't talk about it at a certain point. We just say on the whole real line, this is what it is. Okay? So the next one becomes very important. It's the power rule. What if I have x to the 10th, or x to the 25th, or x to the 5th, or x to the 1? What's the derivative of powers? Now for that, you need to know what's called the binomial theorem. I need to know how to factor. Like if I have x squared minus x naught squared in the numerator, divided by x minus x naught, I have to know how to factor. If I have x cubed minus x naught cubed over x minus x naught, I have to know how to factor. So what we're talking about is powers minus powers over something. And it turns out every time there's a factor. If you write down what that factor is and take a limit, you will get the general statement for the derivative of a power. Now, that's only an integer power. So after today, you're supposed to know if I have the function given by x to the 10th power and somebody says, what's the derivative function? It will be 10 times x to the 9th power. If you have x cubed, the derivative is 3x squared. What do? You change the power down by 1 and you multiply in front of the power down by 1 by the original power. So if x to the 15th, the derivative would be 15x to the 14th. Now, if I just have x, you probably wouldn't think about powers. If I just have x, I don't think of x to the 1. But if I did, then I'd have 1x to the 0 power. And that brings up the question, what's x to the 0 power? So somebody here said 1. What's 0 to the 0 power? Oh, maybe 1. That's the trouble with 0 to the 0 power turns out to require a couple of paragraphs of talk. Okay, so if you just have f of x equals x, and I ask you what the derivative is, it is highly unlikely you will think, oh, it's x to the first power, and that's 1 times x to the 0 power, and let's see, that's x to the 0 power, I think that's 1, and you won't do that. You'll just say, what's the derivative of x? That's an identity function, derivative is 1. That's what we took care of earlier. It works, but you have to make some more definitions if you try. You don't want to make this power rule work for every function you think of. Like, what's the sine function to the 10th power? I don't know. I mean, I know, but it's not just 10 times sine to the 9th power. In other words, you can't just make this. Some people like it so much they make it true for everything. You know, and don't do that. So only if it's x to a integer power, positive integer power, that we know what it is now. But then that gives us all polynomials. And then what I do here, it gets harder. We talk about how you differentiate a reciprocal. Why is that? Because I might want to differentiate 1 over x. 1 over x is a reciprocal of x, you see? So we have, this is the bottom of page 12, is how you differentiate a reciprocal. We want to do that because I want to later differentiate quotients. But first I have how you differentiate negative powers. How do you do roots? What's the formula for roots? And a little bit later down here, we talk about derivative of sine function. And the derivative, and by the way, for 1 second, has anybody had trouble downloading the test? Anybody had any problems? So you know you can put it back and all that tonight. Everybody knows about it. I've had a couple of questions people sent me about it, but other than that, everybody's okay? Home too? Okay. All right, so on these pages, you have derivative sine function, And then we have a derivative of products, and that's not so simple. That's called a product rule. That's more complicated. And then finally, we do quotients and we do composites. So and it's getting close to 20 after. I wanted to show you guys what's in this collection. What this material is covering that I gave you today is the first 2 sections of chapter 2 in the book. Okay. The author talks about derivatives in section 1, and then he does arithmetic of derivatives in section 2. That's basically what some of this is about. So what I want you guys to do after you do your tests and stuff is to read these pages. Also look in the book in chapter 2, sections 1 and 2. And you can go back and forth. You can see how he does things, how I do things. You can decide which you prefer. Okay. I'm hoping that both of them will help you understand. In certain places, I'm much more careful than he is because I go into a little deeper water than he does. That's not necessarily a bad thing. It depends on what's in the deep water. If it's a shark, you got problems. But anyway, I'm hoping that these notes will help you see what's in the book, or that what's in the book will help you see what's in these notes. And of course, I hope for the rest of the semester, you got me around to help you too. So I think what I will do here now is in the screen share, so you guys can see me again. Also stop.